check, see if we can make this happen. Start. Required. Really? Sure. And it's the last day. I think I looked. It's May 2nd. We have our final exam, so I'll put it. How do I have to do this too? Da-ba-da-da-da. All right. No? You don't like that. What was wrong? Okay. And then I have to link it to the LMS in order for you guys to, sorry about that. It's not my favorite part of teaching. It's the top hat, so now I have to go where? 232 settings. Your school hasn't what? Okay, can we do this? Yes. Sure. Almost done. Wow. Okay. Do you guys like see these cryptic source, these codes of the year? Oh, that's easy because it's the only one I think that's easy. Yeah. All right. Does that look like what you guys see on your schedule? 2025-20. I think that's got to be spring 2025 semester. So we'll see if you can find that. Well, good morning. That's how you set up Top Hat. You don't have to know that for the exam. That's how you almost set up Top Hat. Now it's okay. I'm not going to do that. Let's see if. So if I now go in here, I hope that, so you guys need this join code 425867 on the top, and attendance. Look at that. What a great way to start.
Wow.
That's interesting. Do you have anything to do with that camera? There's a little camera watching me. And a phone. This feels like Big Brother. By the way, have you guys, so I was actually going to start our discussion with, have you been paying attention? Well, maybe I should start my discussion with, welcome to class. My name is Dr. Bedars. You're here for electromagnetism. But I wanted to know if you guys have been paying attention to the AI sphere, like what's going on in the world of AI, and to what extent. I mean, I imagine you're getting help on homework from various platforms. It's become a big discussion on my side of the table, like especially imagine teaching online. Like, oh, you can ask Gemini 2.0 how to solve almost any question that you can pose to a student. And it'll give you the breakdown. And if you ask it, well, what about the details of this step of algebra in here? Can you explain? Boom. What does it mean to find the magnitude of a, oh, wow. Okay, thank you. Can you do my homework for me? Can you take my exam for me? Well, it depends. How well is it proctored? I mean, if you want to go crazy, imagine that we decide at Liberty that every exam is going to be proctored in the form of face-to-face video chat. Like, okay, so we're safe, right? No. Because it turns out that AI now, I just read recently that with what they would, however they ranked it, 85% success rate, you could upload, I don't know how much footage they need, of video, like me right now, I'm being recorded. Upload video of my lectures, my discussions, a few of our, I don't know, give it a semester's worth of lectures. And what it'll do is recreate me, an AI version of me, that you can have a conversation with, that you can ask physics questions to. And this is done in minutes. Process time is done in minutes. 85% chance that a human won't be able to tell that it's not you, somebody that actually knows you. You're like, okay, so, and fast forward now a decade. If that exists today, fast forward a decade, we can't proctor exams that way anyway. But I think there's a bigger existential question that it immediately forces upon us, whether we like it or not. And that is, if it can do all the physics that you're trying to learn, all the engineering that you're trying to learn, and it can, and better than you, and faster than you, and oh, it doesn't require a $90,000 a year starting paycheck. It'll do it for the cost of the electrical grid. What does that do to the definition of you as an individual, as an engineer, as a educator, as a member of civilization? What if it's a certain future, unless some craziness happens to derail it, that 10 years from now, anything that you think you have specific skills to do, outside of maybe some really hard to get to manual labor jobs, will be pointless. Like the accountant that my father-in-law pays an accountant to do his books because he owns a company, and praise God, he's always done my personal finances too with this accountant. But who needs an accountant when tax laws can just be uploaded and all your financials, and it can literally read the handwriting off of them, and wow, you filed that in 9 seconds? That's awesome. What's your wage? Oh, it's free. I mean, maybe somebody that provides the service will want to, but the point is you don't need an accountant, so that company, whatever it is you're paying them for the service, they don't have to hire human accountants. But that's not just accountants. That would have been really realistic years ago. It's the mechanical engineer too. Can you analyze this problem for me and run a simulation in ANSYS and do all, oh wow, that was quick. Thank you. Can you redesign it? Because I don't like the, oh, you're done already? Oh, you're proposing an even better design than what I had in mind as your boss. Do I need to be your boss anymore? There are CEOs of tech companies, high-tech companies, and in fact AI-based companies, that realize that at this point they themselves are relatively obsolete because their own technologies could take their jobs and probably do it better and quicker and certainly cheaper. And so what does that leave for us? I've been pondering that a lot. And I've also been watching what the CEOs of companies that have produced these techs have in mind, and they don't have good answers. Surprisingly, the only thing I could come up with was something that I later watched and heard Elon Musk say, and that is that the prices of all goods and services ought to essentially go to zero in a world where humans don't have to be paid to do the jobs. But that is so, I mean, you'd have to restructure everything from, like everything, I guess. The way civilization functions, the way the economy functions, and who exactly would be on top to decide if you don't have any useful contribution to society, well, where are you going to get any money? Is that going to be government handouts, a purely socialized system? And in that case, who says, well, how much do you get? Just enough to survive, or enough to thrive, or somewhere in between? And what if I want organic eggs and chickens that we're eating, or grass-fed beef? I'm sorry, you can't quite have that. We have this is the government-supplied or AI-supplied beef. I don't know what world it leads to, but those questions, we have to ponder them and come up with answers for them, because there is an existential crisis around the next corner, and it's coming fast. I've been playing with AI tech just to see how far it can go, and it's crazy already. All kinds of free services that Google has will do things that'll blow your mind, to the point you're like, I don't think I need to learn how to program a computer, because it writes code really fast to do whatever I want it to. And I'm not telling you to cheat, because I think the answer isn't, all right, I'm tapping out, just turn off my brain and let AI take over for me. I think it's a different view of what we're here to be and to do. And there was a silly song, I can't remember who wrote it or even what most of the lyrics were, but when I was growing up, there was a song about, we're human beings, but we've often been human doings, meaning that we're always just making ourselves busy with stuff rather than focusing on what it is to be human and to exist and to embrace that existence and to do the things that are Christian faith would suggest we do, which is love one another and marvel at creation and give glory to God for it. And it's kind of interesting, in a perfect world, which we don't really live in, unfortunately, it seems like if a technology comes about that takes away from us the burden of existence, the parts about, oh, I need to do this so that I can have food on the table, and so that I can survive and pay the bills and do all the things that we have to do to get jobs, and instead can focus on what I want to do, maybe what I'm made to do and what I have passions for. I think our education will shift from, I'm getting an engineering degree so that I can make stuff so I can earn a paycheck, and it'll instead be, I'm getting an engineering degree because I want to expand my mind in the same way that I want to expand my horizons when I take a vacation. For sure, something that would survive in that new world is, well, I'm not just going to sit at home in my bed and have my robot bring me coffee, so I'm going to get up and do something. I'm going to take a walk in the woods. And now I'm tired of the woods, so I'm going to take a walk. I guess I'm going to take a plane, go to Europe, see the Eiffel Tower, see the Parthenon. And so travel, just for the sake of experience, like, well, if I'm not doing anything, I might as well just embrace existence and embrace the world. And there will be a point where it's like, okay, I'm done with seeing stuff. What's next? How about I just close my mind or close my eyes, and I want my world inside my head to be bigger. And strangely, that's really what education ought to have always been. That it's about self-enrichment and having a new world, view of the world and a bigger picture of what nature is and how things work. And I think that will survive, but not for the reasons that it does now. Right now we don't always get an education for that purpose. We get an education because it's like, well, I guess I need to get a well-paying job. Mom said I need to go to college and get a degree, because without a degree, apparently you can't get a nice job, and if you don't have a nice job, it's harder to attract a nice mate, and it's some stupid sequence of events that suggests that we get education nowadays. But I think it's going to be forced on us soon to do it for the love of it. And if you don't, I don't know what the consequence will be. Maybe nothing. Maybe your world will just be smaller inside your head when you close your eyes and think about things. Maybe it'll be that it has an effect on your paycheck. Maybe it won't. I don't know. Because if you're not a contributor, whether you know stuff or don't, because AI is doing everything, I don't know what it's a weird economy that suggests. But it is definitely a weird world that we have coming, probably within the next decade, I would think. Because the rate at which it's been arriving has been fast. The progress is staggering if you pay attention, and it's not slowing down. So anyway, I spent much of my break pondering AI and trying to picture what I couldn't get from watching videos of people who should have good answers, and I don't know that I like it. It's a weird. I like some of it, but it's weird. It's like I tell people often ask me, like, oh, you're a theoretical physicist, you must love sci-fi. I'm like, no, I've always hated sci-fi, actually. It's been too far removed from my reality to be worth pondering, is kind of my general view. So a sci-fi that I like watching is maybe close enough to our present existence that, in my mind, it's worth entertaining thinking about it, because I could see my world turning into that, so it's interesting to think about. But if it's something crazy like wormholes and all that, interesting physics, not so much. I don't want to watch a movie about it. But now my world is almost becoming sci-fi when I'm thinking of, like, what is the next decade possibly going to look like? I'm like, it might be those movies I don't like. And so I don't know what that means. Maybe embrace sci-fi, because here it comes. But why don't we pray for wisdom and then get to discussing physics? And I might like to hear if you guys have any interesting thoughts on AI, because, like I said, it's been a barren landscape trying to. The companies are super focused on developing this thing so that it can outdo us in every way, and not so much thinking about, and what repercussions might this bring? Like the downfall of civilization. So it's weird, but definitely worth thinking about. All right, let's pray. Lord, I thank you for this group of students. I thank you for just this opportunity to exist. And you know that I've always thought it's strange to exist in the first place, and now existence itself is certainly becoming stranger with the advent of AI. I pray that you grant us wisdom. Wisdom in our day-to-day human interactions, but also wisdom in terms of seeing your hand in all of this, and you certainly have a plan, and this isn't taking you by surprise, and we want to be on top of that plan and part of it, and useful in this world, and maybe just to preach Jesus to a generation that is largely going to be suffering from a huge existential crisis, to let them know that, first of all, life on this planet wasn't the only life that you intended, but however else you want us to play into this picture. Pray that you would open our eyes so that we can see how to navigate through all of it. And in terms of this semester, do help us to learn this physics, not just for the sake of being able to mechanically solve problems, but to appreciate the works of your hands and the laws that you put in place to run this place. And let us get a glimpse of your glory that way. In Christ's name, amen. So do any of you guys have, by the way, insightful thoughts on AI? That anything to add to the conversation? Yes?
I do think that, at least from a business perspective, even though we may use AI to do a ton of work,
Yeah.
we'll always need somebody to fire. Because you always have to...
You said to fire somebody to blame?
At least from
Bad AI.
you need to be able to fire someone if someone goes wrong.
So you keep one guy on the staff.
Unfortunately.
Yeah. Huh. Somebody to fire, somebody to blame. Yeah. It's, any other interesting thoughts?
Okay.
Yeah. Okay. Good.
One is, I think at some point, with the advent of AI, there will come a time when colleges start to have classes on like prompt engineering to get the AI to produce whatever it is that you actually want.
Yeah.
I'm sure you've experienced like using ChatGPT and whatnot.
Yeah.
Sometimes you have to ask it a couple different times in a couple different ways.
Yeah. So I don't know if you've played with, what is it called? I think they just call it Gemini AI. It's a right now a free product, and what they have is the full power of Gemini 2.0 with the ability to tune it to feed new specific set of information that's relevant to your situation, that it'll then add into and sort of bias its responses from, and so it's and now already something like that is out there. And by the way, I don't know how to put this. I mean, like I said, from the educator side, the conversations I've been hearing are really dumb. It's like, oh, they're cheating because they're using this technology. Kind of like I imagine 50 years ago they thought about handheld calculators or whenever they were invented. It's like, they don't know their arithmetic. They're going to go like 2 plus 2, and now they don't have to know what 2 and 2 equals. But the calculator is here to stay. Well, maybe AI will replace that too, but AI is here to stay, and so in that sense, I'm not going to tell you don't use it. That would be stupid. I'm going to tell you use it in any way you can, but I would caution you against using it in such a way that you make yourself obsolete. Meaning, a fantastic way to use AI is, you can, in this version that I was mentioning to him, you can put in audio mode and have a conversation with a world expert on a topic, like back and forth, like well, we're not talking, I'm kind of monologuing right now, but if we were having a conversation, it would be just like this. You can have a conversation with AI. I've done this and it's weird. But you could say, I don't quite understand the notion of the electric field. Can you tell me how I should understand this better? What does it mean for the field to be a vector quantity, a vector field, and what the heck does that mean? How's that different than a normal vector? And you can use it as a study aid. Don't come to office hours anymore. But so free up my schedule. You might as well use it for the things that'll benefit you as a student, and that certainly is one of them. Or not, please solve this problem, cut, paste, but you've been working on the problem for 20 minutes and can't figure out how to solve it, and dang it, it's 12:30 and you better not, you don't have my phone number, but so you're not going to get a response from me for the next 9 hours, but what if you want to stay up till 2? You're like, okay, here, Gemini, that's how you do it. Thank you very much. So you're enriching yourself rather than short-circuiting your education. You should definitely consider using it in that way, because if you just decide you're not going to jump on the bandwagon, you'll be left behind, especially as techie people in techie majors. Is it correct that almost everybody here is engineering? And a few, who's not engineering? Remind me again, is there any of you? Anybody not engineering? Not a single one of you. Oh, interesting. All right, well, welcome you engineers. I was once upon a time an engineer until I was saved. No, no, I was an engineer until, it was actually pretty close timing, coincidence. Junior year, I did switch majors. I also found Jesus. So it was, but I don't think it was for one and the same reason. Yeah. So the first chapter in our tech, do we have to go over the syllabus, or you just want to look? You can look over the syllabus if you have questions. We can discuss it. How much time have I blown? First chapter is all about some basic things that you probably have known about for lots of years, but not in the way that we want you to. And among those things are, what is charge, and where do you find it in nature, and what is a field, and that's maybe not a topic that came from middle school. But if we started with charge, how would you describe charge if somebody just asked you the question on the street? Oh, you're a science engineering major. What's charge? What kind of answer would you give? I mean, probably, I might, if I rewind to last semester and pose a similar question like, what is mass? How would you answer that one? Because most of the time we're just in the business of giving a value for it. Oh, something measured in kilograms, but what is that something? Can you describe it for me? And if we start with that one, what's the answer, or what would your answer be for that question? What is mass? Yeah?
Just the existence of matter.
Yeah, that's an interesting thought. The existence of matter. How do you know that it exists? Yeah, you pick up a physical object, and you're like, I don't know. But it's troubling though if you played particle physics games and tried to figure out, like, okay, here's an iron dumbbell. Can you show it to me? Yeah, and I mean show it to me not like you see it in the gym, but put it in front of an instrument and try to find those subatomic particles that make it up. You'll be very disappointed to essentially find nothing but invisible fields. And those fields don't act anything like things that we know of, in the sense of having discrete locations in space. And any of the individual particles that make up that iron dumbbell, if you pull them out and try to figure out what is their nature, what was it? I think the year before last year, by the way, the physics PhD was given for the people who, brought about AI. But the one before that was given for the guys who finally proved that at the quantum level, things don't exist in what they call local realism, so that you can't actually say in a real way that a particle like an electron exists here. They don't. They exist everywhere until they're measured. And it was previously just a suggestion that, theoretically this makes sense. We'll think about it as a distribution function, and then the science and the experiments went to the point that, like, nope, we're sure. They literally don't exist like that. And so if you've ever thought about, like, what is an electron, and you're thinking about, oh, this little pinpoint small thing, like, sorry, that's not what it is. It doesn't behave that way. It gives you that impression sometimes, but it doesn't work that way. But that brings us back to what is mass. You're like, well, your idea of matter is, we at least have this idea that this isn't very massive, but when you hold massive objects, it tends to be that bigger masses makes it harder to cause things to change directions, or the velocity vectors to change. So make them go from nowhere to somewhere, in terms of velocity, to push a car to get it moving, to get it to stop, to get it to turn. There's this sensation that goes along with that, at least. The bigger the mass, the harder it is to nudge the thing to go a little faster, or to force it to make a left turn. And that's really an operational definition, meaning that in practice, this is how I would try to measure mass. You could also say that, well, given a planet like Earth with a gravitational field, things tend to be tugged toward the planet in proportion to their mass, and that's another way that you could give an operational definition of mass. But when you look for it, that's the point when things become really weird. Like I said, you can't find stuff. You find that a piece of iron is almost entirely vacuum, with the exception of invisible fields. And what content you really find is energy of those fields. And it's the energy of the fields that, when it's localized, gives us this sensation of mass. And it's weird, but that's the way that it works. So I mean, sometimes the answer is, what kind of definition do you want? Operational definitions of charge. I was, just by chance, I should have taken a video of it, but my daughter had her birthday 3 days ago, 7th birthday, and so I blew up a lot of balloons. And in the winter air, balloons in interaction with the dry air tend to acquire a charge. We'll talk about how things acquire charge, but you have a charged balloon and you have a daughter that even if she has no charge on her, that charged balloon is going to be attracted to her. And it was a helium balloon, and this was yesterday, so 2 days after, it wasn't floating much more than like just a little bit more than staying still. But if you walked up to the balloon and put your hand a few inches away, and it could be like 5 inches away, it would start coming toward you. And so much of the morning, she's doing this, like dodging balloons, and it was fun. And I didn't have the opportunity to talk about Coulomb forces with her and the nature of charge, but it's neat what it does. And so an operational definition of charge, just like mass, is this tendency for things to have some quantifiable characteristics so that they can push or pull on each other. But you have to realize, if I do draw a really naive picture of an electron, here it is, and the symbol, by the way, is an E with a minus sign. So there's an electron. The electron has a mass, and it has a charge. So this is, mass obviously is, sorry about my handwriting is bad because I found out years ago, and maybe I have a problem with character. I think I'm impatient with my hand. And so I'm like, come on, write it. I want to move on. And I'm thinking at this point I should be more patient with my hand so that I could fix the problem. But in any case, what's interesting is electrons have both mass and charge. And mass of an electron will interact with the mass of other particles gravitationally, so it'll pull itself toward protons. It'll be pulled toward planet Earth because of the mass. But that has nothing at all to do with this other characteristic of charge. The only thing that happens, due to that charge is, well, if there's something else nearby that has charge on it, then it's either attracted or repelled to that something else. Like if I put a proton over here, so put some positive charge over here. Now, because of Q, by the way, why do we use Q instead of, M, mass? Wait a minute. The Q for charge. There's a problem with the letter C, right? What's the problem with the letter C in physics? Speed of light, right? It's kind of a reserved constant. So, and these are scalars, so we can't say, oh, because it's a vector, I can just use a vector C and know that it's not the speed of light. Well, it doesn't work that way because charge is a scalar quantity. So instead of calling it C, we call it Q. And I haven't really thought about what other cultures do, but anyway, get used to it. Q is charge. So because of the charge on the electron, that's why it tends to be attracted to the proton. And of course, we have another strangeness. When you think about gravity, you have some massive, an asteroid here, planet Earth, that it's about to destroy over here. And gravitationally, they're attracted to one another. When the sign of M, obviously it's positive mass in both cases, and as far as we know, we don't have negative masses. And that's true of, if you're thinking like, what about antimatter? It still has positive mass. So gravity, when you have positive M is attractive as a force. This is attractive, this electrostatic force. when the charges are opposite, negative electron, positive proton. You know that from whenever it is it middle school, when they tell you opposite charges attract. So that automatically suggests that if I had two positive charges, positive charge, what are they going to do? Can't do the same thing. So they repel. And so in that sense, the electrostatic behavior of charges is the opposite of gravity, meaning that when we look at the math, there's going to have to be a minus sign. When you look at the expression, when you look at force of gravity, universal gravity, if you remember from mass 1, mass 2. Do you guys remember from at least my students what the form of this expression is? If you do it as a vector expression, meaning you take position vector 1 minus position vector 2, what you have to have in the denominator and the power of the sign. Anybody happen to remember how that works out? That's all right. So this is, sorry, I need to have a subscript over here, on 1 by 2. So think about this as on, due to, or by. So if you wanted to know, let's say this is gravity, obviously. So let me go, I'll just call this mass 1 and mass 2. So, and in this picture, let's suppose I make a coordinate origin right there. Can you guys roughly see what's going on? Here's a vector, position vector 1, we'll call it R1, position vector 2, R2. So we have to first wonder, did I get the sign right on this? The functional form of this is correct, and we'll get to the details of that in a little bit. But since I want to be sure that the force is attractive, did I get it right? Meaning, should I have to put a minus sign here or not? And how would I know? And so if, by the way, the way that I wrote out this expression, 1, 2, 1, 2, 1, 2, I don't have, and 1, 2, not that it matters with the scalar product of masses. But the sequence, it just makes it real easy to write out. You don't have to wonder about what was the order because it's the same as the subscripts. And so this is supposed to represent the force on the one on the left labeled with a 1 due to the one on the right. And so this math ought to give me this guy. So this is force on 1 due to 2. And of course this one, how would that be labeled? Yeah, so that's the other one. And of course if I did that, then I'm flipping that, I'm flipping this, and I'm flipping this. Which of those flips actually matters on the math part? Which would, if I reverse these guys, does anything at all change? No. What about these two? Well, inside the brackets it does, but it's a magnitude, right? So, okay, that doesn't matter anymore. But these are regular parentheses, so the vector difference, that one matters. So the question is, the only directional side of this expression comes from here. There's where the direction comes from. And of course, that isn't a unit vector, but whatever the direction of this R1 minus R2 is, that's going to tell me it's going to dictate the direction of the force. So in the picture where I have R1 and R2 drawn, where is the vector R1 minus R2 going to be if I put it in the schematic on the left? Where would I find R1 minus R2? Say it again? Well, what if I wanted to draw it in such a way that it's somehow related to, like I made a triangle out of R1, R. Yeah, pointing, and the important part is recognizing, and I hope this doesn't make a mess. Let me use purple maybe, and I'll try to draw it a little bit small. So here's the R1 minus R2 vector. And if you, maybe one way to think about that is if you remember vectors like A and B, if A plus B equals C, then the idea is that I ought to be able to take vector A, stick B wherever A left off, and extend out wherever it goes, and that if you take that tip to tail sum, that it's equivalent, C would be start at the first one, end at the last one. It's, goes along with this picture. And so if we thought about that, you could imagine that you did something similar, like if I take vector R2 and then I add R1 minus R2, so A plus B gives me C, right, in analogy with that picture, then does the math work? Is it true that if I take this plus that I get this? And of course, you're like, well, symbolically, R1 minus R2 plus R2 has to equal R1, which is correct. Wouldn't be correct if I turned it the other way. Then I'd have a mess on my hands, right? Does that make sense to you guys, I hope? Yeah, I mean, it's true that if this direction to the left is the difference R1 minus R2, then it's true that this plus this expression gets me an R1, right? Which is obviously where we're ending up. So was I right or was I wrong on my sign? Is my gravity equation right? That's correct. And why no? Yeah, we know that F12 is supposed to go this way because it's attracted to whatever I think I called it Earth, to the right. And the only thing that gives me a direction in this equation is pointing leftward, and I go like, oh man, save the day. Flip the direction. All right, so there it is. Well, this course isn't about gravitational fields, but there's a super strong analogy between this and electrostatic fields and forces, and that is that when we're talking about this picture, or either one of these pictures, how do charges push and pull on each other? The answer is the same, except the same but different. These positive positives attract, these positive positives repel, so this guy isn't going to be needed for the electrostatic case. So if we put this together, like what's the same and what's different? Well, the universal gravitation constant is going to become a different constant that just takes on a value 4 pi times 10 to the minus 7 Newton meter squared per Coulomb squared, but I'll write that down in a minute. But same form. Let me just do this part of it. So if you look at the equations, this part, identical. This part, exact same mathematical form, except product of charge instead of product of masses, different fundamental constant relating the strength of the force. And crucially, obviously you don't have to write the positive sign in there, but no flip, because if we imagine that this situation was talking about electrostatics instead, I wanted this guy to be pushed leftward away from the other, if that was a positive charge, then leftward was the correct direction. You guys seeing that? But that tells us a lot, the fact that forces of electrostatics and forces of gravity have the exact same mathematical form. Then you get the sense of, okay, so the force decreases with distance. And what possibly isn't obvious is that this is an inverse square law. Because what does it look like? It does. It looks like an inverse cube law, doesn't it? But how could we convince ourselves that it's actually an inverse square law, meaning a force that dies off in proportion to the square of the separation distance? You see any easy way to coax that out? Yeah. You could. Yeah, so suppose that I make a substitution and I just say, what should we call it? How about I just call it R12, some new variable that's equal to the difference. And I rewrite this. And so let's just say F12, K, Q1, Q2, like, oh, okay, so parentheses suddenly become R12 vector over R12 vector's magnitude cubed, right? So what would I then do along the lines of what you were saying?
You would divide the R12
Yeah, so I think what you're kind of doing in your head is the fact that this guy can be seen as its magnitude times a unit vector in its own direction, right? Yeah. And so if we do that, any vector, if you have a vector just to 3i plus 4j, right? So what's the magnitude of this guy? Yeah, magnitude of this is 5, which is, how would you calculate it? 3 squared plus, first component squared plus second component squared, and of course I chose those numbers because the answer is 5. And so, and what is the unit vector in the direction of A? Say it again. 3/5. Sorry, I didn't hear the fifth part. I guess I'm going to write it like this. 3i plus 4j over 5. So look at what's happening here. This is the original vector, right? So this is a vector over a magnitude, right? Which means if this equals this, that I can certainly trip over wires while telling you that this is also true. So the magnitude times the unit vector is the original, which is exactly what we've done right here. This is shorthand for magnitude of, right? And so the point is, if I make this substitution in here, now I get something that says k, q1, q2, magnitude, losing space, I'll put it right here, sorry about the crowding, unit vector over magnitude cubed. So what can I do with this guy and this cubic one? Obviously I can cancel one of the powers, right? And cancel this magnitude and turn this into a 2. And suddenly that gives me k q1 q2 over r12 squared. And I need a direction, and that's the whole purpose of this guy. It's a unit direction, though, so it has nothing to do with the strength of the force, just the direction of it. But then it's clear that what matters is, well, how big are the charges? There's a direction that we already know about. It's going to force positives apart and opposites together. But it shrinks in proportion to the square of the separation distance. Why did we write it that way? It makes the math easiest. When I said, hey, suppose one charge is located at this coordinate, another charge is located at this coordinate, what's the force on this one? Well, it's easy when you just, here's the coordinate of one, here's the coordinate of the other, and crunch the numbers and do the math and get the answer. Whereas, realize that the burden would be different if we wrote it in this form. And a lot of books, it's probably your book actually, that is going to give you a form that looks something like this. The burden is then like, well, what do I put in the place of r12 hat and an r12 vector? And then you have to really do what we did backwards. Like, oh, but this really represents the difference vector. And I have to take its magnitude and find its unit direction. And so I think, even if the book consistently does something like this, I think for the sake of actually working out problems with numbers, like coordinates for the particles, I'd highly recommend doing this version. The inverse, the one that looks like an inverse cube, but really is still telling you that the force is an inverse square law. So just like gravity, a long way to say it's an inverse square law, double the distance, and electrostatic forces, at least between point charges, will drop off by what factor? If they're take balloon and daughter, and well, it's not really true in that case. We'll get to that later, but if daughter was point particle and balloon was too, and you double their separation distance, how much weaker is the force then with an inverse? 4 times, and triple it, it's 3 squared or 9 times weaker, and so forth. So that's the way we should expect electrostatic forces to behave. That's the way we expected gravitational forces to behave, but the trouble this semester is that something interesting happens in nature with gravity. Well, maybe we should have a different discussion about gravity. We don't know really how gravity works. is the real answer. And that has profound consequences on theoretical physics and cosmology. There are very heated ongoing debates about the structure of our universe. Whether we're back, by the way, if you haven't heard, to wondering whether the Big Bang ever happened, when it happened, whether it's happening in an isotropic and homogeneous universe as they've supposed for the last 5 decades or not. So maybe gravity's a bad one, but the idea with, where was I going with that? Electrostatic forces dropping off inverse square cubed. What was I saying just before I went on my brief? Gravity. Yeah, so electrostatic forces, at least we know how they work. But the answer is weird. But it's worth asking. You know, when I was going back to what is the value of education apart, you know, in a post-AI world, I hope that it's just so that you can enrich your appreciation of nature. At least that's a big part of the answer. And until AI does take your job, I mean, I guess it's good if you can apply that understanding of nature to do things. But the answer that you come to when, like, well, first of all, Newton came up with this expression for the gravitational force, and he was wise enough to understand that that is not an understanding of gravity. You know, he could calculate the trajectory of Jupiter's orbit and was not at all disillusioned by somehow believing that he had, you know, accomplished what mankind had not done for millennia before him, which was understand how gravity works. Because that's an equation. It tells you nothing about how does Jupiter even know that the sun is there such that it should be attracted to the sun and cause its trajectory to deviate as it goes through space. He was wise enough to recognize that there needed to be a communication mechanism. And we thought in about 1915, when Einstein came up with his general theory of relativity, that we had the answer, and now it's dubious. I don't know if we do or not. We might. It's a mess. But so we don't really have a good answer yet. We might. And you've probably, if you watch nerd videos like I've done for my whole life, but not sci-fi nerd videos, you've probably seen about the distortions of space-time and all that, and long discussions to be had about why that doesn't satisfy everything else in the world besides gravity. I shouldn't say world, universe. So the communication for gravity we don't quite have a good grasp on, but the communication for how does an electron know to be attracted to a proton, or how does a balloon know to be attracted to daughter? The answer is light. But strangely enough, not the kind of light that you could measure with a photodiode or some kind of a detector that you put between the two objects. It's light of they call them virtual photons. It's an abstract form. It basically, on the quantum mechanics, looks like one of the imaginary solutions to the math, but has all the characteristics otherwise of being a photon. And what's interesting is we didn't invent that. It fell out of the math. And we're like, oh, what is that? Oh. They call them exchange particles. So this idea that there's some sort of an exchange going on. What are they exchanging? These virtual particles of light between Jupiter and the sun, back and forth, in proportional to their luminosity, which is mass in that context. And so you have this picture of this non-detectable version of light. Maybe you could think about these virtual photons are the means of the communication. And if it's right, you're like, oh, but light takes time to travel. Even these virtual photons only travel at the speed of light, and so we ought to be able to find delays in gravitational effects at large distances. So of course, experiments were done. There are delays. And so we know that what falls out of, we find delays in gravity, we find delays in electrostatic forces, but it's a strange picture that we get to see of nature when you view in and ask, like, yeah, but how? What's really going on? And I have this, I don't know, I ride my bike a lot, and that gives me a lot of time for undistracted thinking. And I don't know if that's good or bad, but over the years, when I have to contemplate weird things and teach them, if you want to take modern physics, we get to have some cool discussions. I really wonder, I don't know if you've heard this, and this will be maybe a final comment. I know you're pretty much ready to go, but a lot of the world's most influential science, techs, industrial, now AI company leaders often, periodically get together and they have conferences where a big focus, and I think I told this to you guys if you had me last semester, they have meetings where the whole agenda is, I want to figure out if this is a simulation. Like, am I stuck in some simulation due to, and they seem to rarely focus on, well, who wrote it, if it is. But they just want to know, like, this is too uncanny. Like, what the heck is, why can I move these things? And where did I come from? I woke up and now I'm conscious. It's like, enter, done, object created. So is this a simulation? And serious individuals who are otherwise functional in society have these discussions and really want to know, and they debate it, and they propose their viewpoints, and then they usually have a vote. And they usually vote about 50-50. And so, if you want to put it this way, some of the leading minds that govern civilization today can't even decide whether there was a mind behind this or not. And about half of them are convinced that there is. And at first you read that like, they're lunatics. But to me that just speaks to exactly what I believe in the first place, and what you guys, I think, believe as well. This is a product of the mind of God. And whether that's a real thing or not, whether it's essentially information being exchanged with my mind through my hand, or whether it's substance as you've always thought of it, is completely inconsequential. Whatever it is, it's for the glory of God, and it's certainly spoken into existence. And speaking is information, it isn't stuff. And I think it's at least interesting that when we look for that stuff that seems so real in laboratories, it's not there to be found. But what you do find is this kind of stuff, information, rules. It's like rules govern nature, and you can't find the things. You find the rules between these seemingly existing objects. But every time you look for the objects, it's like, where in the heck did it go? And it doesn't even have local realism, as we found out 2 years ago, and Nobel Prize was awarded for it. So I'm all for it. I'm like, yes, it is a simulation. Who made it? Who wrote this? Yahweh. He has a name. And that, I think that's a fine view going forward. If that allows me to sit down and Elon Musk is one, I think, that biases that, yeah, this definitely is a simulation. I'd be happy to sit down and be like, I totally agree with you. Who do you think that was? I mean, what kind of character wrote this program? You and me, and for what purpose? And those are, I think, obviously the questions that come afterwards. If this is simulation, as you want to call it, product of God's mind for his own intentions and purposes, why? What role do we have in it so that I can fulfill my calling? Obviously serious questions that we ought to all entertain constantly. But so anyway, great simulator. Grant us wisdom. All right, see you guys Wednesday.